a NASA space telescope has made an unexpected discovery at Comet 3 I/Atlas, and the finding has sparked significant excitement within the astronomical community. What initially appeared to be just another observation of a passing interstellar comet has now become a major scientific breakthrough, one that could reshape how scientists understand the evolution of comets and the chemistry of planetary systems beyond our own. The excitement does not stem merely from what was discovered, but from the extraordinary circumstances under which the discovery was made. Comet 3 I/Atlas occupies a unique place in scientific research because it does not belong to our solar system at all. It is an interstellar visitor, one of only 3 such comets ever detected, and its arrival has given astronomers a rare opportunity to study material left over from another star system entirely. The comet was first discovered on July 1, 2025, and from the moment its interstellar nature was confirmed, researchers around the world began mobilizing every available tool to gather data before it disappeared back into deep space. Unlike typical comets that are bound to the sun's gravity and follow predictable elliptical orbits, 3 I/Atlas is not gravitationally captured by our star. Instead, it travels through space on a hyperbolic trajectory, a path that indicates it originated far beyond our solar system and will eventually leave it again. This fact alone makes it an object of immense scientific value. While thousands of comets from our own solar system have been studied over the years, the opportunity to examine a primordial object from another star system is extraordinarily rare. Scientists estimate that 3 I/Atlas may be at least 7 billion years old, making it possibly twice as old as Earth itself and the oldest comet humanity has ever observed. This age suggests that it formed during the earliest period of its parent star system, likely before that system's planets were even fully formed. In other words, it is a surviving fragment of ancient cosmic history, a relic untouched and unchanged since the early universe. Because of this, astronomers are particularly eager to analyze its composition, structure, and behavior. Studying comets from our own solar system already provides insights into the conditions under which the planets formed billions of years ago. Studying an interstellar comet amplifies this potential, offering clues about the planetary construction processes occurring around distant suns. The comet's journey near the inner solar system has been challenging to track, especially when it moves behind the sun from Earth's perspective. Yet even then, scientists have managed to observe it using spacecraft positioned around Mars. These rovers and orbiters have been able to study the comet during times when it was hidden from Earth-based telescopes. Every available scientific resource has been brought into play, emphasizing just how important this fleeting opportunity is. The most significant development, however, came from a research team at Auburn University in Alabama. These astronomers succeeded in pointing NASA's Neil Gehrels Swift Observatory, a space-based telescope normally used to detect gamma-ray bursts, toward Comet 3 I/Atlas. The Swift Observatory has a unique advantage over ground-based telescopes because it is positioned above Earth's atmosphere. It can detect ultraviolet light that never reaches the planet's surface. Ultraviolet radiation is absorbed by our atmosphere, meaning many of the chemical signatures astronomers want to measure are invisible from the ground. Using Swift's ultraviolet imager, the research team detected a faint glow around the comet. This glow was the unmistakable signature of hydroxyl OH gas. Hydroxyl is formed when ultraviolet sunlight breaks apart water molecules, and its presence is considered one of the most reliable chemical fingerprints of water ice sublimating from a comet's nucleus. In simpler terms, hydroxyl detection means the comet is releasing water vapor as it warms, just like comets from our own solar system do. This discovery is particularly important because it marks the first time scientists have detected this water-related signal in an interstellar comet under such precise conditions. Previously, the only interstellar objects observed, such as 1 I/Oumuamua and 2 I/Borisov, provided limited or ambiguous water-based data. Detecting hydroxyl gas in 3 I/Atlas gives researchers a solid foundation to begin analyzing the comet using the same techniques applied to solar system comets. This means they can study its activity levels, thermal evolution, and chemical behavior in a familiar scientific framework. Understanding how a comet evolves is crucial to unlocking the secrets of planetary formation. In our solar system, comets are believed to contain some of the most primitive material left over from the time the planets formed. As they travel closer to the sun, they release frozen gases, including water, carbon dioxide, and other volatile compounds, that reveal what conditions were like billions of years ago. This outgassing provides a chemical map that researchers can interpret to understand early planetary chemistry. The fact that 3I/Atlas exhibits the same water-driven activity as solar system comets suggests that its parent star system underwent similar processes during its formation. This is a groundbreaking realization. Until now, astronomers had only indirect evidence that planetary systems across the galaxy shared common chemical building blocks. The detection of hydroxyl in 3I/Atlas is direct, observable proof. It demonstrates that water-rich comets, which may have delivered oceans to young planets, are not unique to our solar system, but may be a common feature in planetary systems everywhere. This finding also opens the door to studying the chemical diversity of interstellar materials. If future observations of 3I/Atlas reveal the presence of other volatile molecules, such as carbon monoxide or organic compounds, scientists will be able to compare these substances to those found in solar system comets. Such comparisons could reveal whether the early chemistry of distant stars resembles our own or whether other systems evolved under significantly different conditions. Even small differences in isotope ratios or organic content could provide new insights into the nature of planet formation across the galaxy. The scientific community is already considering how this discovery might influence future missions. Some researchers have suggested designing spacecraft capable of intercepting interstellar visitors like 3I/Atlas before they leave the solar system. Others believe the discovery strengthens the case for developing advanced observatories capable of studying faint ultraviolet signatures from Earth's orbit. The Swift Observatory's ability to make such a detection, despite not being originally designed for comet research, demonstrates how versatile space-based telescopes can be when repurposed for unexpected events. Another remarkable aspect of the 3I/Atlas study is the collaborative nature of the observations. Scientists from multiple institutions, countries, and space agencies have worked together to gather data on the comet. Mars-based spacecraft provided information when Earth-based telescopes could not. The Swift Observatory captured ultraviolet data unavailable from the ground. Ground observatories filled in gaps when the comet was visible from Earth. This multi-platform approach represents the future of astronomical research, especially when studying rare and fast-moving interstellar objects. The discovery at 3I/Atlas also highlights the importance of remaining flexible and adaptable in scientific research. When the comet was first discovered, no one knew whether it would provide meaningful data. Interstellar objects are notoriously unpredictable. Some disintegrate quickly, others show almost no activity. But by acting quickly and using the full range of available instruments, astronomers were able to seize a rare opportunity. The detection of hydroxyl gas might never have occurred if researchers had waited or limited themselves to traditional comet studying tools. Now that the presence of water-related activity has been confirmed, researchers will be watching the comet closely throughout its journey. They hope to track how its outgassing changes over time and how its chemical emissions evolve as it moves farther from the sun. This could reveal whether interstellar comets behave differently than solar system comets, or whether their thermal and chemical evolution follows the same patterns. Ultimately, the significance of the Swift Observatory's discovery extends far beyond cometary science. It provides a direct window into the chemistry of distant planetary systems. It offers evidence that water, one of the essential ingredients for life, is not confined to our corner of the universe, but likely widespread across the galaxy. And it reminds us that the universe still holds countless secrets waiting to be uncovered, often in the most unexpected places. Comet 3I/Atlas, a frozen traveler older than Earth itself, has become a messenger from another world. carrying ancient clues across the vastness of interstellar space. Its brief visit to our solar system is giving astronomers a chance to look back in time and glimpse the processes that shaped not only our own world, but countless others scattered throughout the stars.